Hello everyone, welcome to my presentation on proactive geosteering for GeoConvention Virtual Event 2020. This presentation is provided by GazServ Incorporated, an advanced remote geosteering company partnering with Beloy Petroleum Consulting. My name is Ghazanfer Zahid and I am president of GazServ Incorporated. In this presentation, I will walk you through a successful case history on proactive geosteering that brought cost-effective results with the cost-saving solutions to the client. Let's go to the next slide and see how the project was and what were the objectives and how we did the cost saving for the client. Now here is the project overview. The client planned to drill number of horizontal wells with the objective to keep the horizontal wells 1 meter above the reservoir base. So below reservoir it was shale and the reservoir was sand. The directional drilling company provided gamma ray and resistivity data in real time to steer the wells proactively. So before starting a project, we conducted post-well analysis on nearby horizontal wells data and came up with initial recommendations to the client. And that was also a pre-well analysis for the upcoming well. And after drilling first horizontal well, we conducted a detailed post-well analysis with more curves, the memory data from the LWD tool. We came up with improved recommendations to the client for optimum and proactive well placement solution that could save their drilling time and cost. So here's the client's geosteering guidelines for us. The objectives were very clear: to place the well 1 meter above the reservoir base and with the tolerance window of plus minus 0.5 meter TVD above and below. And minimal shale tags were required and that were limited to 3 to 4 per horizontal section. And horizontal section was about 1500 meters. And the second objective was to keep the wellbore profile very smooth as well to run the completions. And for that, the dogleg DLS provided to us was less than 5 degrees per 30 meter. And 3 to 4 shale tags, proper shale tags with gamma ray increase was requested for the base confirmation. And there were two types of drilling environment. There, one was sand on shale, which was the first pad, and the second pad was sand on sand. That was more challenging, and that was the second part that had to be drilled after the first pad. Okay, so before going further, let's take a look on the wireline logs, how they look on vertical plot. This one is the gamma ray on the left track in green color. The second track we have porosity. The red one is the neutron porosity. The black curve is density porosity. In third track we have two resistivity curves. One is black, which is deep resistivity curve, and one is blue, which is shallow resistivity curve. And you can see that there's a thick green line, solid green line on the section which represents the reservoir base. So just above the base you can see the gamma ray is low and below it is a shale. And one more thing you can observe here is the calcite stringer just above the reservoir base. So that's why we had to place the well above the calcite stringer, and the calcite stringer was identified on porosity, although we didn't have porosity or density data in real-time well. So we had to find it out on the gamma ray and resistivity that how it looks like. We found that the calcite come up with the low gamma ray and high resistivity values, and you can see one more calcite layer here, so it's high resistivity, low gamma ray. So it was characterized by these features on logs. So the target criteria, there was also sidetrack criteria set by the client, which we can see that here 75 meters, more than 75 meters in shale or transition zone or above the target zone could result into the sidetrack. So let's look in the next slide at how the first well was steered. So here's the cross section of the first well, geosteered with 3 planned shale tags. In this cross section, you can see there are two tracks. One consists of gamma ray in green color. And with gamma ray, there is a red dashed line, which is a gamma ray cutoff. And above that, on the second track, you can see there are two resistivity curves. The blue is the deep resistivity curve, and the red color is the shallow resistivity curve. And below, in the bottom part of this cross section, you can see the red bold thick line, which represents Wellbore profile. And there is a yellow zone behind, which was the target zone, and below that it's shale. So whenever we were approaching the shale tags, we had to be very careful to make the wellbore angle very gentle, avoiding the boundary exit, controlling the ROP. And you can see here on the gamma ray plot that there are three times we have seen the um, reservoir boundary. We touched it, we didn't penetrate, but we just scratch it just to confirm that we are very close to the bottom. So every 500 meters we have to go for this shale tags. And this was a 1350-meter lateral section that was drilled in 46 hours. Before going further into the detailed analysis, let's review the difference between the reactive and proactive geosteering. So by definition, reactive is something being responsive to something, while proactive is being prepared even before an incident takes place. I've created here three examples for you to understand it very well. In the first example, the gamma rays sensor is 18 meter behind the bit, so you can see the reaction time once you see the gamma ray spike. At the same time, the bit is already 18 meter inside that zone, and when you're trying to come out, you may lose 50 meters or more of vertical section or the reservoir section. In the second example, which is better than this previous example, the gamma ray at bit. When we say gamma ray bit, it means like 2 to 3 meters, sometimes 5 meters behind the bit, and the reaction time is faster once we see the bit. Once we see the gamma ray increase or gamma ray change, we can make the decision, and the bit is almost like 3 to 4 meters inside or 5 meters inside that zone. So that's also always quicker. We can lose it. We can avoid losing the reservoir section. In the third case, you can see there is gamma ray and resistivity tools, which are 17, 18 meters behind the bit. But we didn't touch the boundary here because the resistivity tool is seen deeper. It has deeper depth of investigation, so it can even detect the boundary before hitting it. We can make smoother decision, no dogleg, harsh doglegs, a smoother wellbore profile, and it's staying all the time 100% zone. So this is the difference between the reactive and proactive geosteering. Let's boundary approach analysis. So for that, we have to take a closer look at the shield tags. The slide is zoomed in the shale tags responses and explains how we made geosteering decisions in real time in our first well, taking into account the resistivity tools polarization. You can see here anisotropic effects while approaching the reservoir bottom boundary. And there was an additional challenge there. We had a calcite stringer just at the boundary. So it was mixed up the signals, the responses of the resistivity was mixed or masked with together with the calcite and the bed boundary approaches. So we have to be very careful, and we were trying to understand with this on this real-time responses. And this was the step just before do the final post-well analysis before getting the memory data. How we do the post-well analysis. Our post-well analysis is like a 4D approach, and that's the fourth dimension actually, or the so how we do it, as we said that from the very beginning, we are doing the pre-well study. That's what we have done before starting the well, and do the pre-well modeling afterwards. And then third step was real-time geosteering, and the work is not yet finished. We are going for the fourth thing, which is post-well study, very important for future wells, fine-tuning of the reservoir, and the understanding of the tools responses and what to do and how to do. That gives us a good learning uh, through the post-well analysis. And in this specific case, we had MFR resistivity tool, that's a standard resistivity tool, non-azimuthal, and we received 12 logging curves, 12 resistivity curves, 6 were phases, 6 attenuation, and there were two frequencies in the tool, 2 megahertz and 4 kilohertz, with three spacing transmitter receivers, spacing 20 each, 30 inch, and 46 inch. So this post-well analysis is always helping in the right selection of the curves for the accurate well placement. So this slide explains our three-step methodology to conduct post-well analysis. The first step requires QCing of LWD curves, sorted them in different tracks, and investigate to choose the right curves for real-time transmission. The right selection of curves helps in accurate well placement, so we have to be very carefully sort out the resistivity curves accordingly and look for the best curves, ideal curves, and why two curves? Because sometimes the LWD companies have limitation of providing only two real-time curves to make decisions. So the right curves will help us in making better geosteering decisions. And that's the step two for our post-wear analysis methodology, where we plotted two curves together to understand which one is better and filter out the unnecessary curves here. So you can observe here the horizontal distance of early warning detection at an approaching boundary with different curves plotting. In step three, we plot the qualified pair of curves in the cross section to pick the best one at approaching boundary. And when we are having confidence that which one would be better, we recommend those curves to the client that this would help us better making the geosteering decisions proactively. After the full post-well analysis, we come up with a better solution and conclusion to the client. Like in our case, we had earlier using two curves, which two resistivity curves in real time, and that were deep phase, low frequency, and the shallow phase, high frequency. So after doing full analysis, we found out that shallow phase, low frequency should be better, and deep attenuation, high frequency would even be better. So this combination, we have replaced the initial set of curves. And we found that with those curves, we can reach the following benefits like early warning while approaching the reservoir base, so we don't have to actually touch the boundary, we just can detect the boundary even before hitting it. And polarization was very clear and distinct to make quicker and better decisions. With careful interpretation, the recommended curves, the one that we have recommended, um, our curves allowed us for early detection of up to 1 meter above the reservoir base. So just above 1 meter above the reservoir base, we are start detecting boundary. So it is always better to avoid the shield tags, and we can stay just in zone while utilizing the best curves. So on subsequent wells, we propose that the shield tags can be avoided using our recommended curves, and boundary approaches were considered only as a confirmation of reservoir base, and that was confirmed by the client as well. Now, this slide shows the second well of the implementation of our recommendations. And the two new resistivity curves were even way better, and we found that the well was geosteered within the pay zone without even getting shale tags, and we know that we are very close to the bottom boundary. And the well was geosteered without the shale tags, no boundary exits, and very smooth wellbore profile. So, and the boundary was confirmed on the resistivity responses that you can see over here. There are two, three responses. So these bed boundary responses confirm that, okay, we are approaching, we are very close, like half meter or less than that, close to the base boundary, and we went up again without touching anywhere. You can see it on the gamma ray. So overall, the 1325-meter lateral section was drilled in 36 hours. However, the first well was drilled. Its length was 1350 meter, and that was drilled in 46 hours. So you can see here in we have saved almost like 10 hours of drilling. 10 hours means 22% of drilling time was saved in lateral section, and that saved a big cost for the client because subsequently and for the future wells they had to drill with this more methodology, better methodology, and they could have saved time. Then here we talk about the second pad, where we said that earlier it was sand on sand reservoir type, drilling type. And in that reservoir, the client wanted to use the deep azimuthal resistivity LW tool due to the challenges of sand on sand drilling. And there was no significant variation in the gamma ray as well, so it was really difficult to go with the standard resistivity tool. So once we received the resistivity data after drilling the first well with the high end tool, deep azimuthal resistivity LW tool, it had 158 curves, including azimuthal data, up, down, and directional signals. And it had three different frequencies: 2 megahertz, 400 kilohertz, 100 kilohertz. And there were four different space transmitter receiver spacing: 30-inch, 46-inch, 56-inch, and 76-inch. So the tool could even see way deeper inside, and the azimuthal data could be of greater value. However, after the first lateral was drilled with high-tech LW tool, a detailed inspection, or sorry, the investigation was carried out to determine the need of the expensive tool in the reservoir, because if you are going with this azimuthal rescue tool, they are generally very expensive in the market, and we wanted to save the cost for the client. So analysis on that deep azimuthal rescue tool. So after plotting all 158 curves, you can see there's so many curves in that tool. It's a very advanced tool, high-tech tool with a lot of images as well that could receive in real time. But again, we had limitations to get three or five number of curves in real time, so we had to pick which one is the best. And it was found, after all this detailed analysis, what we found that non-azimuthal resistivity tool could be effectively utilized to geosteer the required intervals. And we recommended client to go back to the non-azimuthal resistivity tool, and we can geosteer your all wells on this pad as well without utilizing this deep azimuthal tool, and we could potentially save big cost for you. Here's the summary of our proactive geosteering, how we save drilling time and cost. So in first we mentioned that we saved 10 hours in every lateral section. That was the 22% of the drilling time, by avoiding the shale tags and smoothly placed well within the accurately placed well in the target zones with a smoother wellbore profile. So overall, what we found that the doglegs we had in our wells was ranging from 1 to 2.5, even not reaching 5 degrees per 30 meter. And we found that okay, we not only placed the wells very well within the target zone, but we also avoided all the unwanted zones. Most of the in-zone statuses shows that our well bore placement was better than 85% to 95%, sometimes 100% in zone, and there were actually near to um, some 70-80 wells. And the ROP was never been compromised while drilling those wells, so it was always above 100 meter per hour, and we didn't have to ask them to reduce their ROP just because we are approaching the base or something. So there was no risk, low risk decisions, and better decisions, informed decisions. And so in the first pad, they saved a lot of cost on the drilling time actually. And in the second pad, we advise them to avoid using the azimuthal LWD tool, because we could successfully confidently utilize the as a non-azimuthal resistivity tool, and that also saved a huge cost to the client for their next so many wells. So this is always like a balance between the best geosteering plus the optimized cost as well. So we are not only optimizing the well placement, but we are also optimizing your cost and your time, which is also important for the client. So let me conclude my presentation here and just with the final words that yes, what we do, we have extensive international and domestic proactive geosteering experience with an excellent understanding of advanced LW tools. So if you have like Halliburton's ADR, Baker Hughes EasyTrack, Schlumberger's Periscope, or Weatherford's GuideWave as another LW tool, we can help you geosteer your wells with well-informed decisions. And our purpose is not only the well placement, but to make a smoother wellbore profiles as well for re-entry wells or for future wells or the well completions. And we help reducing the drilling time. And objective is to advise you that what tools you have to go for. You have to you can we can advise you to reduce your unnecessary LW tools as well, and can give you alternative cost-effective solutions. So we have a full package of optimization. So just let's get back to us with your data, and we'll provide you the right solution. Thank you for watching my presentation. And if you have any question, send me at gazanfer.zahid@gasserv.ca as written on the slide. So I'll get back to you shortly. Thank you very much again, and we'll see you coming back with your data. Goodbye.